Welcome to today's video tutorial on building robust data processing pipelines using Apache Beam. If you're interested in transforming and processing large data sets seamlessly, you're in the right place. Before we start coding, let's get a brief overview of what Apache Beam is. Apache Beam is an open-source unified model for defining both batch and streaming data parallel processing pipelines. It allows you to write data processing tasks in Java, Python, and Go, which can then be executed on various execution engines such as Apache Spark, Google Cloud Dataflow, and Apache Flink. Now that we understand what Beam is, let's set up our environment. First, ensure you have Java Development Kit, JDK, installed on your machine. You can check if it's installed by running Java version in the terminal. Next, we'll need Apache Maven to handle our project dependencies and builds. If you haven't installed Maven yet, you can download it from the Apache Maven website. We will create a new Maven project. Open your terminal and execute the following command. This command generates a simple Java project structure. Navigate to the project directory using cd beam data pipeline. Next, open the pom.xml file and add the Beam dependencies. We will be using the SDK for Java. Under the Dependencies tag, add the following. Now that we've set up our project, let's move on to creating our first pipeline. We'll start by defining a simple pipeline to read from a text file and write the results to another file. Create a new Java class named datapipeline.java inside the src/main/java/com/example/beam directory. Here in line 1, we import necessary classes from the Beam SDK. Lines 3 to 5 declare the data pipeline class and the main method, where the execution of the pipeline will occur. Next, we create a pipeline object with pipeline.create. The apply method is used to define each step of the pipeline. In the first step, we're reading lines from a file named input.txt. After reading the lines, we apply a transformation to convert each line to uppercase using the map_elements transform with a simple function. This function takes each input string and returns its uppercase form. Finally, we write the transformed strings into a file with the text.io.write method, specifying the output file prefix as output/result. Note that Beam will append a suffix to this name because it saves the results in multiple part files for scalability. To execute our pipeline, make sure to place an input.txt file in the root of your project. This file should contain some test lines. Now run the following command from your terminal. Once you run the pipeline, check the output directory. You should see your result, 00000 of 00001 file containing the uppercase versions of your input text. In this section, we've built a simple data processing pipeline that reads, processes, and writes text data. Let's move on to more advanced features of Beam. For instance, we can incorporate filtering into our pipeline using the filter transform. Let's enhance our pipeline to filter out lines that do not contain the word Java. Update the datapipeline.java file with the following code. In this modification, we insert an additional apply step labeled as filter lines, utilizing the filter.by method. The Lambda function checks if each line contains the substring Java. By including this filter, we ensure that only the relevant lines make it to the uppercasing step. Next, let's talk about windowing. Windowing allows you to group elements based on a time factor, which is particularly useful for streaming data processing. For instance, if you are processing logs that arrive continuously, you can window them by time to analyze them in manageable chunks. We will add windowing to our pipeline by importing the necessary classes. Update datapipeline.java to include the windowing logic. In this edition, we use the window.into method to define a fixed window of 1 minute. The following step, count.globally, counts the number of words in each window. The results are then formatted to display a string that shows the total word count. Windowing can be used for both bounded and unbounded datasets, making it a versatile tool when processing real-time data streams. Each window can produce results every time it closes. Next, let's touch upon state and timers, which are powerful features in Beam. They allow you to maintain state information in your pipeline and trigger processing based on specific event timings. This is critical for event time-based processing and streaming pipelines. To illustrate the use of state, We can implement a simple example where we keep track of status changes of a user based on incoming data. Let's use a user status event stream as our dataset. We can create a stateful doFn that will hold the user's status and react to new events accordingly. In the class user status processor, we define a state variable using @stateID. This variable holds the user's current status. In the process element function, we read the current state and make decisions based on the new incoming event. Timers work alongside states, allowing us to trigger actions based on time passed since an event. This can be crucial in scenarios such as session timeouts or response monitoring. You will need to add some code for timer handling as well. In this snippet, we're setting the timer to trigger an event 5 minutes from the current time. You can perform cleanup or send alerts when the timer triggers. This setup lets you maintain a stateful application that reacts to incoming events dynamically along with time-based decisions. While state and timers allow for advanced processing capabilities, we'll also want to ensure our pipelines not only work correctly but are also efficient. One way to achieve efficiency is through the use of the Parto transform, which allows you to apply custom logic through user-defined functions. Using Parto.of, we create a doFn where you can specify your logic for processing each element independently. This offers versatility and allows for complex operations or transformations of the incoming data flows. Remember that this execution is done in parallel, contributing to performance improvements. Next up, let's talk about testing our Beam pipelines. You should always aim to validate your data processing logic through effective testing strategies. Apache Beam provides testing utilities that can help you write unit tests for your transforms. In the Data Pipeline Test class, we define our test pipeline using testpipeline.create. We set up input data using create.of, apply our transformation, and finally assert that the output matches our expectations using passert.that. It's crucial to ensure that tests are comprehensive and cover a variety of cases. Testing not only confirms that our logic works, but also protects against regressions in future code changes. Make sure to run your tests frequently during development. Now that we've covered a substantial amount of material regarding pipeline construction, transformations, windowing, state, and testing, you're now equipped to build custom data processing pipelines tailored to your needs. In conclusion, Apache Beam provides a powerful framework for writing data processing pipelines. Whether you're handling batch or streaming data, Beam gives you the flexibility and tools needed to get the job done efficiently and effectively. Don't forget to subscribe for more tutorials on data processing and software development. Join the conversation below by sharing your thoughts or questions regarding this video. Thank you for watching, and happy coding!